this talk, I'm Nobuyuki Matsumoto and from Weekend BNL, and I will talk about a comment on the subtlety of defining real-time path integrals in lattice gauge theories. Here, the real-time path integral is recently revisited for the interest in real-time dynamics of quantum theories, especially their non-perturbative aspects. For example, the creation and evolution of jets in heavy ion collisions, and evolution of the universe in very early stage, and also non-equilibrium properties of quark-gluon plasma. And Monte Carlo calculation has been successful in non-perturbatively evaluating Euclidean path integrals. However, there exists an infamous sign problem in the application of Monte Carlo methods to real-time path integrals. So this is the ordinary expectation value here expressed for the Minkowski action. Since the integral is highly oscillatory because of this phase factor, the Boltzmann weight, we typically need exponentially large sample size for precise estimation. However, for this sign problem, recent numerical developments have made us accessible to evaluate the real-time path integrals via numerical calculations. For example, in the complex Langevin studies, there has been an applications to real-time Yang-Mills theory, real-time Yang-Mills theory, and also for the contour deformation techniques, including Lefschetz-Tembo methods. There has been studies for the Schwinger-Keldysh formalism for quantum mechanics and quantum field theories, and also real-time scalar field, real-time Yang-Mills theory, and real-time quantum mechanics. Also, without using Monte Carlo, there has been studies with tensor normalization group for real-time scalar field. And here, therefore, it is becoming of practical importance to establish an appropriate way to evaluate real-time path integrals. Here, our primary interest is in dynamical properties of QCD. And QCD on the lattice, we know that the H field takes value on a compact group. However, it has been discussed that real-time path integral with compact variable requires care. And it was pointed out by Languth Inomata that we need to implement I epsilon in the real-time path integrals, and this was discussed in the context of non-relativistic quantum mechanics. The points are that the discretized path integral is not well defined exactly on the epsilon equals 0 in the continuum limit and taking the continuum limit, and the need of I epsilon can be seen from the asymptotic expansion of the modified Bessel function. And recently, the unitarity and convergence in the lattice for the lattice gauge theory has been discussed. And here, the Hoshina, Fujii, Kikukawa developed Schwinger-Keldysh formalism with the transfer matrix, real-time transfer matrix, respecting unitarity using character expansion. And Kanwar and Wagman proposed alternative actions to the Wilson action, removing divergences with contour deformation. And here, also Patolahi paper for a discussion on unitarity in these theories. Here we'd like to clarify that we can use the conventional lattice gauge theory actions, in particular Wilson, but by properly implementing the I epsilon. And it is here important that the I epsilon should be implemented both for time-like and space-like plackets. And we know that such I epsilon is essential to obtain the causal structure of the green functions in continuum. However, it may seem uncertain why such I epsilon is required starting from the lattice theory. We thus would like to further clarify that the I epsilon can be given a physical meaning of removing singular paths having non-trivial winding for an infinitesimal time evolution, which do not have corresponding path in the continuum. And these point of views are only apparent in system with compact variables. And these are the important remarks on this study. Here, the Kanwar and Wagman's idea was the following. Since the path integral is not well defined at epsilon equals 0, they first deformed the integration contour assuming finite positive epsilon in such a way that we can take the epsilon to the 0 limit even for finite lattice space in A. And they clarified how the relevant variables can be separated, especially with character expanded and or heat kernel actions depending on gauge group. And they constructed the contour deformation and argued the corresponding Jacobian. And as they addressed the unitarity of the real-time transfer matrix, they concentrated on the epsilon in the kinetic term when constructing the contour deformation analytically. And they showed that the deformation techniques works perfectly for 2D Yami's theories. However, as we argue below, the asymptotic expansion analysis explains the need of I epsilon also for the spatial plackets. On the other hand, the method discussed in this work is the following. For several epsilon positive finite, we calculate the A to the 0 limits of these observables, and we take the epsilon to the 0 limit to obtain the final estimate from these continuum limits for finite epsilons. And the unitarity in this case becomes a feature that we expect to be recovered in the epsilon to the 0 limit. And the epsilon method turns out to be only applicable when the theory is sufficiently close to the continuum. And from the estimate of the applicable beta from 2D, we seemingly face the critical slowing down in the practical 4D simulation. Thus, contour deformation similar to Kanwar and Wagman's are desirable once incorporating all the epsilon. And in this work, no Monte Carlo result is presented. So I finished this introduction part and would like to move to the latter part of the talk. We first begin with 1D quantum mechanics, which is a typical system having this subtlety. We first review the so far discussed subtlety of compact variables in quantum mechanics, this model, and discuss the need of I epsilon from Hamilton formalism. And then we move to the Yang-Mills theory. And we first discussed the subtlety of real-time path integral in lattice gauge theory, and check the convergence properties of Wilson action. And we repeat this argument for the Yang-Mills theory here. So, and we end with summary and outlook. I move into this part. This is the simplest example having the subtlety, and it is a particle in a periodic box. This is the action we consider. Here, phi is the angular variable in S1 here. And this can be mapped to ordinary quantum mechanics in a periodic box with a mass of this mass by introducing a spatial extent L, and the ordinary X will be defined like this. So yes, this will be the spatial extent and this will be the X coordinate. And the Hamiltonian will be given in this form here. P phi is the conjugate momentum phi. And the momentum eigenstates are the plane waves. And these diagonalize the Hamiltonian to give the energy eigenvalues in this form. And we define the transition amplitude from the level Ni to Nf for time with the time capital T like this. And we can, so since this diagonalizes the Hamiltonian, we can tell that this is equal to this one. But here we would like to know how this equality can be obtained via path integral. And the naive discretization of the amplitude gives this form of the path integral. Here, u0 is just e to the I n naught, e to the phi naught times ni, and similarly to the capital N. And here, I discretize the time with a step size A and introduced U1 variables at time slices L. And here, the fields on the fields in the exponent is defined accordingly to this discretization like this. And here, the action S is the placket-like action, like this. So this will give the delta phi squared. And the du is the ordinary Howell measure. This integral can be analytically performed using the character expansion of this form.
Excuse me, sorry. Could I
Yes.
ask on the previous slide, just trying to understand the path integral you wrote?
Okay.
I'm hopelessly confused. So for instance, there's a u sub 0 factor and a u sub n factor. Why are these things exponentiated?
I'm sorry. Okay. So the
I guess these are just the eigenfunctions on a circle, e to the I and phi. You know,
exactly.
the eigenfunctions of the. So
Oh,
what
and then to
equals
get
ni and then phi.
amplitude expectation value.
Yes, the momentum eigenstates are expressed like this in the phi, with the phi states. So I put it over here. This is e to the I phi. And it is.
I gotcha. Thanks. Okay, it's clear. Thanks.
Thank you very much for the question.
May I follow up with another question?
Yes, please.
Why is it that in the action you have the difference between u's and not phi's? Is just because you use u's as your variables? I mean, is this a derived expression or it's something that you postulate here?
I think the discretized action is not unique, but I hear the periodicity in the phi direction. I wanted to make the periodicity in the phi direction preserved, and the easiest way I thought was introduce this U1 variable, express everything in terms of U1 variable, and integrate them over the Howell measure. With that answer.
So the advantage here, I guess, is you're avoiding the kink when there's a difference of pi, right?
Yes.
Okay, very good.
And also make it similar to the lattice action. Okay. Yes, so this is the character expansion. The character is just a u to the n power of u, and the in are the modified Bessel function. We can use this orthogonality relation to invert, to check the coefficient is given by this modified Bessel function. So this real part of u gives the cosine part, and u to the minus L gives this part. And this is just a Howell measure. And therefore, the previous lattice action will be re-expressed in this form. I expanded the Boltzmann weight in terms of these this formula here. And then by using this orthogonality, we see that here u0 appears here and here. So there will be a delta, Kronecker delta for n I and n naught. And there will be also a line of Kronecker deltas, and like this, and it will be multiplied by the product of the modified Bessel function. But since these ends should be identical, it will just give a power of n. I'm sorry, here the summation is assumed, and we obtain this expression. This was a derived amplitude, and this is analytic for all beta, for all beta or complex beta for finite lattice spacing, but it's not in the a to the 0 limit. And this can be understood from the asymptotic expansion of the modified Bessel. So this is the formula, and here please note that here appears the exponential factor, and also over here, but this will be suppressed when z takes value on the real axis. So for this region of z over here, the second term is completely ignorable according to this exponential factor. However, when the argument of z is minus pi over 2 over here, which is the naive real-time case, as we see from here, this second term equally contributes to the first term, because it will not give a damping suppression. Therefore, this discretized amplitude behaves differently depending on how we take the Minkowski a to the 0 limit. I mean, if we take the a to the 0 exactly on this line, we need to incorporate this second term. But if we take the epsilon to the 0 limit, we approach to this limit from this side, we can ignore the second term. So that makes the difference.
Sorry, could I ask, so is it sufficient? Let's see. So I'm going to pick a path towards a equals 0 and take the limit. And you say I don't want to do it along the crossed out, what color is that? Green and red line there.
This one. Yes.
Is it sufficient to take any like small angle?
What means, like small angle?
So like, I wish I could wave my hands wildly at you. So the bad direction. Sorry, is that the real axis, the vertical axis there?
This is the real. I mean, this is the real axis. This is the imaginary axis.
Okay, yeah. Sorry. So for A, ordinarily we're going to take a to 0 along the real axis, along sort of from the right. If we take a equal to proportional to 1 plus I epsilon, but then take epsilon and a smaller at the same time and linearly, is that sufficient? Or is this something like, no, I really need to approach from almost pure imaginary in the limit?
So just to clarify, I thought that the real axis, if you take beta to be real and positive, it seems to me that the a goes to 0 comes along this hashed contour that, pointing towards minus negative infinity.
Yeah.
So I think that's the naive real axis that was considered. Not the horizontal one, it's the vertical one that goes down. Sorry, I also don't know exactly what you're pointing to, Scott, when you're asking.
Yeah, okay, got it. So Andre, there's an I in the argument of the Bessel function. The complex plane plotted there is the argument Z of the Bessel function, and that's why everything's rotated.
Yes, I think so.
Yeah. No. So yeah. All I'm saying is I'm going to take the a to 0 limit, and I'm going to take the epsilon to 0 limit. And is it only a problem if I directly approach a equals 0 exactly on the crossed out line, and any sufficiently small deformation, even if the deformation is getting smaller as I go towards the origin, is sufficient? If we can't understand the question, then we can move on, because maybe you answer it later.
I think the next slide also addressed your question. But
Okay, yeah, sure, go ahead.
I would like to emphasize that this expression is analytic for all beta complex for finite A. So any small deformation for finite A is okay, as long as the spacing A is finite. But it becomes different in this limit. So that is the point. Yes. And here, and the okay, and the okay, and this okay. So the correct continuum limit, it can be obtained with introducing the epsilon. So here I need to first modify this naive discretized amplitude in this form, and then we can use, so, and we would like to consider the a to the 0 limit for this quantity, and then now we can use for arguing a to the 0 for this quantity. We can use we can now use the expansion for in this region. So this region, so we can neglect this second term. And then here, this I naught is a normalization factor, which will be absorbed in this capital N. And by dividing I naught, then this I and F will behave like this, according to the previous asymptotic expansion. And we know, when we then notice that this is 1 plus A to the capital N type expression, so we can take the a to the 0 limit and obtain this exponential. And this was the, okay. And therefore, by first taking a to the 0 while keeping epsilon finite, we obtain this discrete, we now tell that this is here, we already introduced the I epsilon. We first take the a to the 0 limit and then epsilon to the 0 limit and obtain this correct amplitude. And therefore, we need to introduce I epsilon in path integral to obtain the appropriate continuum limit. And without I epsilon, the unphysical part of the asymptotic expansion, I mean the second part in the previous slide, a second term in the previous slide, gives severe oscillation. So, okay. And we're not, it does not correspond to the correct continuum limit. Okay. So, okay, then I would like to further discuss about this I epsilon. Although the previous argument explains the need of I epsilon mathematically, it may be uncertain why such I epsilon is physically required to obtain the continuum theory. Here, we would like to argue that starting from the Hamiltonian formalism, this I epsilon can be given a physical meaning of removing singular paths that have no corresponding path in the continuum. So this is just the ordinary Hamiltonian formalism quantum mechanics. But here, U and P phi are taken to be referred to as the canonical operators. Here, U, please note that U is not the time evolution operator, but here rather similar to e to the I phi operator. And the commutation relation we impose is this expression. And U is the configuration basis, and whose eigenvalue relation is given like this. And N is the already introduced momentum basis, and the inner product will give U to the N like this. And here we may naively consider the Feynman kernel for a time increment A, like this. And the meaning of naive we will address momentarily. And Hamiltonian, Hamiltonian we introduced previously as 1/2 beta p phi squared. And inserting the momentum basis, we see that this wave function part gives this part, and the momentum part gives this part. And we here take phi and phi prime to be in this range. And the reason for I'm calling naive is the following. We argue below that we need to introduce also for in this case introduce I epsilon to obtain the kernel for an infinitesimal time increment A as a limit of the kernel for a finite time increment A. So here we ordinarily take this A to be finite, but we eventually would like to obtain the expression for an infinitesimal time increment. But to obtain that, we actually need I epsilon, and this expression lacks this I epsilon, so I call it naive. Okay, so this was the obtained kernel. And this quantity is actually not well defined for finite A, let's space A. The reason can be seen that from the mathematical fact that the Jacobi theta function given in this form is only analytic, is known to be only analytic for imaginary power tau positive. And please here note that here this is summation of n over z, and the n squared structure is the same, and n linear structure is also the same. So this can be rewritten in terms of the theta function here. However,
sorry, can I ask, when you say that that quantity isn't well defined, do you mean that sum doesn't converge, or just that the function isn't analytic and we'd like it to be analytic? I mean, that seems like a perfectly well defined sum to me.
Is here, okay, please refer to this right figure. This is the theta function, and in which we take the imaginary part tau equals to 0. However, I truncated the summation to n smaller than the summations of integers smaller than n. And here I'm increasing the n value from n equals 10 to n equals 100 and 600 and n equals 1000. And we here see that inclusion of large n components makes this quantity oscillatory and also singular. And actually, it's also it seems to be divergent. And inclusion of yes.
So you say the sum actually doesn't converge at finite A?
I don't think so.
Okay.
I'm sorry. So it doesn't converge. Yes.
Yeah. Very good. Thanks.
Thank you for the important comment. Input question. So, and here I would like to comment that here by a special scaling of tau, after introducing another scaling variable L, and so tau proportional to 1 over L squared, we have an analytic window at delta phi is over here, this one. At delta phi over the order 1 over L, so a very small window, actually vanishing window when we see this in delta phi space, which corresponds to the infinite box limit of quantum mechanics. So these are messy equations, but essentially just saying about the ordinary momentum relation in a Fourier momentum, discrete and continuous relation. And with this scaling, this is n equals to 1000 curve. So the gray curve, so the gray curve over here. And so I took the same n value for the gray curve over here. So this curve, but there is no this kind of oscillatory singular behavior over here. And the infinite box limit is for comparison by this magenta line. So we have this analytical window, but for the ordinary, without this scaling, it seems that we do not have analytic function at all. And the reason of this singular behavior becomes more apparent after Poisson resummation. In this case, gives what is known as the Jacobi identity. So this was the amplitude. And I just argued that this is not well defined. But after the Poisson resummation, you obtain this well-known this form. So here W over Z, summation of W is a summation over the winding number connecting phi and phi prime during the time interval A. And this is because this part should correspond to the velocity squared, and in the time interval small a, so here I have phi and phi prime, and so W0 sector gives this amplitude, and W1 sector gives this wrapping around amplitude. So this is the multi-winding contribution. And here, quantum fluctuations larger than 2 pi has been argued as physically not meaningful, especially in this context of compact variables. And this is based on the observation that quantum states should be described by the position on the ring S1, therefore by the pair, these pairs, but not the phi themselves. And winding or the transition history would be an emergent concept in classical limit. And in particular, in our case, if the path winds non-zero times during a finite A, for a finite A, it winds infinitely in A to the zero limit. And therefore, such paths therefore do not have corresponding path in the continuum. And we can see that the inclusion of these unphysical paths making the expression not well defined. And here the physical path can be extracted by implementing the I epsilon as previously. So the correct prescription is to implement epsilon to the zero limit outside and introduce I epsilon just in the previous argument. And then the windings, the paths having non-trivial windings will drop off because even when phi primes and phi are close, this integer part gives a large contribution. And therefore it projects to this physical path like this. And this flow function like expression is just saying that it is it projects out the physical non-winding path contribution. Okay. And we have obtained the correct continuum limit with the I epsilon. So this was the kinetic Boltzmann weight part. So this is the discretized expression, and we can formally write this in the A to the zero limit as this well expected form. But here this is just a comment, but here phi is formally treated as taking values in the universal cover, just to make this expression simple. Okay, and we can actually recast this procedure from a point of view that is similar to chiral symmetry on lattice. counting on universality, the global structure of the field space, I mean the compact or uncompact, should be irrelevant in the infinitesimal time evolution. However, we can only deal with finite spacing A in constructing the path integral, as discussed here. And for finite A, we will correctly see the global structure. So the IEPS, but we do not want to see this when taking the A to the 0 limit. And the ipsilon here works as hiding this global structure as taking A to the 0 limit at the level of finite A. And here, please note the ordering of the limit. It is essential to use the formula for the kernel, so this one projected on to the physical path, in which we assume that A is infinitesimal to drop the winding contributions. And we thus first take A to the 0 limit, keeping epsilon finite. And accordingly, we take epsilon to the 0 limit outside the path integral, so over here, after taking the A to the 0 limit. Namely, real-time path integral for compact variables is not a simple summation over phases, but the epsilon to the 0 limit of the summation. And I epsilon thus should thus be regarded as a part of definition of the real-time path integral and has the physical meaning of removing singular paths. I just now finished the quantum mechanics part, and the Yang-Mills part turns out to be just a generalization of this. So this is the Wilson action for the Minkowski spacetime, and we hereafter assume that the gauge group is SUNC for simplicity. And here I just treated the spacetime non-uniformly and introduced the spatial lattice spacing A and the time increment A naught. And I just flipped the sign, to match the F squared coefficient, to match the sign of the F squared coefficient. And as it's well known, we can expand the Boltzmann weight in terms of characters like this. So chi r is the character, and dr, just for convention, is the dimension of the representation r. And the character coefficient CR is known to be given in this form. And this is a complicated expression, but essentially this is the wild character formula for U and C. So here epsilons are the diagonalized matrix U. So yes. So these are the U1 variables. Epsilon I are the U1 variables, and the summation can be obtained by inserting the periodic delta function to the UN integral to make it just the SUN integral. And the integration of this phase variable will give the modified Bessel function, and then this denominator power will be cancelled by the van der Waals determinant from the measure. So this is the Boltzmann weight, and this was the character expansion for each of these factors. And the character coefficients was obtained in this with the modified Bessel function of these form, with this form. And since beta goes to 0 in the continuum limit of asymptotically field theories over here, we again confront the problem of the asymptotic expansion of the modified Bessel function as in the quantum mechanics model. In fact, if exactly using the Minkowski signature on lattice, the appropriate continuum limit would not be obtained. And for this, we introduce slight imaginary parts as previously. And here, please note that the sign is different, but the sign for the time-lapse packet can be justified from the Hamilton formalism, as we will argue later. And the sign for the space-like plackets can then be chosen from the argument of Lorentz invariance to match the asymptotic formulas, asymptotic expansion formulas, except for the overall sign difference coming from the this 0 and I sign difference of f squared. And then this sign agrees with those given by the ordinary I epsilon in the continuum theory. So what here is extracting from the asymptotic expansion is just the same physical part of the expansion as in the quantum mechanics. So the rule of thumb is just try to extract that the first part of the asymptotic expansion by this I epsilon. So I first would like to check the convergence properties of the Wilson action. To confirm the convergence properties related to the I epsilon, we consider the SUN, in particular 2 NC equals to 2 or 3, Wilson theory in 2 dimensions. So here since it is 2D, we only have one time-like plackets, and we here treated the spacetime uniformly. So I said A not equals to A, and beta t is given by this expression. Here G is dimensional, and we said G equals to 1 in the following. So everything is measured in the unit of G. And on the lattice L times tau sized Wilson loop, so the physical area will be given by capital A equals to L tau A squared, is well known to be given in this form with the characters of the trivial and fundamental representations. And for this quantity, the continuum limit is known from the analysis of the heat kernel action. So Menotti and Onofre give this string tension with the heat kernel action expression of the continuum limit for string tension, and Kanwar and Wagman show that this is we can use this string tension and give it to be the phase factor. Okay. So this is the expectation value of the Wilson loop whose physical area is 1 for various epsilon. And here I calculate this directly using the modified Bessel functions. And left side is the real part of this Wilson loop, and the right side is the imaginary part of the Wilson loop. And here I'm increasing the lattice spacing in this way, in this direction. So this blue curve is for the epsilon 0.1, and I'm increasing epsilons, and the oscillation part will be the appearance of the oscillation part will be delayed after increasing epsilon. Here, please note that for relatively large lattice spacing, I mean in this region, in the asymptotic expansion picture, the unphysical part of the expansion, I mean the second part, unwanted second part, contributes and gives this oscillatory behavior. And therefore, given lattice spacing A, in turn, so we discussing here, we need to prepare epsilon large enough such that the unphysical part can be neglected. And for the studied range of the lattice spacing here, the beta t and the product of beta t and sine epsilon, because it is introduced in the form e to the I epsilon, should be larger to 4.5 for SU2. And here, please note that instead of implementing this I epsilon, we may expand the action with characters in advance and replace this modified Bessel function part with the physical part of the asymptotic expansion. And the corresponding result with epsilon equal to 0 is shown with a cyan dash line, but here it is on top of the epsilon 0 limit black line here and here. And it is plotted for the region where the asymptotic expansion gives us sufficient convergence up to machine precision. And with safely setting epsilon 0, it reproduces the a to the 0 limit. So these are just for the completeness. I check the a to the 0 limits, and the epsilon to the 0 extrapolation gives the correct continuum analytic, reproduces the correct continuum result. So this is the a to the 0 extrapolation. Actually, everything is a function of a squared here. So I just fit the real parts with the linear function of a squared. And we fit 5 points here for each epsilon with a function of a squared. Yes. And epsilon to the, I further extrapolated these points. So these are finite epsilon values. Yes. And extrapolated this to the epsilon to the 0 over here. And this black dashed line is the exact epsilon to the 0 value from the heat kernel action. Okay. So we fit the quadratic and cubic function of epsilon, and I use the cubic result for the central value and the difference from the quadratic value as the estimate of the systematic error. And the obtained estimate agrees with analytical value with this estimate of the systematic error. And I would like to comment that I actually found a mistake yesterday on the plot. So the values on the preprint was slightly different from what is shown here. These are the plots checking the finite A effects and finite epsilon effects. So the black one is the a to the 0 limit for fixed epsilon, and the a to the 0 convergence is rather non-trivial, and the difference becomes larger for lattice large area A. And finite epsilon effects also we can expect that it differs more largely for large area, and it is also observed here. So finite epsilon effects becomes larger for larger A, so we may need a more careful analysis when using these values of A. This is the same study for the SU3 case. Okay. And we here also need to prepare epsilon large enough. In this case, beta t times sine epsilon is greater than 15. For the unphysical part can be neglected. And in this, for SU3, the asymptotic expansion actually did not converge up to machine epsilon in this study range of A. So I did not plot the corresponding curve here. And doing the same epsilon to the 0 extrapolation study, we obtained that we produce the non-analytical value. I'm sorry for the lengthy sentences, but I'd like to make some remarks here. And as mentioned, to avoid the oscillation, epsilon should be prepared such that it reduces the unwanted oscillatory part. And since the characters are expressed with beta r, also in the 4-dimension case, these values, these estimates should give a rough estimate of the required epsilon also in higher dimensions. However, the large bounds over here are unpleasant for 4D case because of the critical slowing down. A similar situation occurs for the character replaced action. The divergent asymptotic expansion gives a sufficient approximation up to machine precision only for a comparably large beta r, especially for SU3. And therefore, though our method gives a way to obtain the appropriate continuum prediction it is desirable to circumvent the critical slowing down or develop an action that is convergent at small beta r, for example, by contour deformation. And the second remark is that here, please note that when we use the character replaced action, the exponential factor appearing over here is common to all the representations and will be canceled in expectation values. I mean, after taking the ratio of the partition function and this the integral for the operator. Then the remainder is actually an expansion of g squared. So it is 1 over expansion of polynomial expansion of 1 over z, and 1 over z is g squared. And gauge invariant observables can be re-expressed by characters in various representations. And since the character coefficient for the placket is now replaced by an expansion of g squared in this form, in this replacement, the expectation value of the observable will be correspondingly be given as an expansion of g squared. And this is nothing but a perturbative expansion. In this sense, the character replaced action may not be a good option for performing fully non-perturbative calculation, though it should give practically good estimates. So, I would like to move to the epsilon from Hamilton formalism.
Nobuyuki, just to warn you, we're at 55 minutes, so we should try and wrap up before, yeah.
I'm sorry, yes, thank you for the reminder. Okay, so I will repeat the argument given for the quantum mechanics case. So we here use for simplicity SU2 Wilson action as an example and follow the conventional Hamiltonian formalism. Here we consider the formal A not to the zero limit, keeping the spatial spacing A finite. And to avoid complications from gauge symmetry, we take the temporal gauge. So I take the spatial links to 1. And then at time slice t, we hear the degrees of freedom is the spatial link variables uxi. And to describe fluctuations from uxi, we introduce the local coordinates theta in this form. And with this theta, we can rewrite the Lagrangian in this form, and we can read off the conjugate momentum, and therefore we obtain this Hamiltonian. Again, the ux and p are the canonical operators, and we impose this commutation relation. And configuration bases are, again, in this form. And it is actually, it turns out to be useful to introduce another basis which turns matrix elements. So this is just a tensor product state. And the J, when we take the inner product with this U matrix, it returns the matrix element in spin J representation. And this basis satisfies the complete relation according to the Peter-Weil theorem in this form. We need a dimension over here. For finite eta, this ei eta p shifts the value of u in this form. So this is just saying that pa theta over here. I shifted u, the matrix elements of u, according to the p variable here. And p are the differential operators such that if it acts to the e to the I theta ta, it gives ta over here to the left. And in particular, this pa squared is the minus of the Laplacian, and at theta equals 0, it simply gives this, and therefore the matrix element of p squared is given by just the we need to just multiply j and j plus 1 to this matrix element. Again, the naive Feynman kernel is given in this form. So here p squared is now replaced by j plus 1, and the wave function part is now replaced by this character. And this is just a dimension for coming from the completeness relation. And it will be simplified after introducing the maximal torus degrees of freedom of time-like plackets. Namely, I'm just diagonalizing this time-like placket in this form. This bracket part can be expressed in this form as follows. I drop the subscript x and I for simplicity. So this dimension part is treated by the derivative, and the character are replaced by sign. And I further rewrote it with the e to the in delta phi and e to the minus in, like this. Okay, here n is the n is 2j plus 1, and with this, combining these two summations, we have summation over whole integer z, like this. So we have similar structure of the theta function, and therefore we need to introduce I epsilon again here. Then the previous bracket part will be expressed with the theta function. Now here is I epsilon, so it's well defined. And after applying the Jacobi identity and then dropping the contribution coming from fluctuation of delta phi with non-trivial winding that vanishing the a naught to the zero limit, we obtain this expression. So, and final contribution comes from the fluctuation of order delta phi or the a naught according to the factor over here. Therefore, these tedious factors can be simplified with this observation, and this kinetic term part will be just a trace of the time-like placket as expected. Yes. So now the amplitude is thus derived in the desired path integral form with the I epsilon. And despite the complications related to the field theory, the basic structure is the same as the quantum mechanical model. And one needs to get rid of non-trivial winding contributions for an infinitesimal time evolution with I epsilon. And this I epsilon should thus be regarded as a part of the definition of the real-time path integral. Okay. I'm sorry. Okay. There are just 3 more slides, including conclusion outlook. Please note that since we only have considered the formal a naught to the zero limit, the I epsilon for the spatial plackets have not appeared in the discussion. In fact, in this treatment, the characters for the spatial plackets can be expressed in terms of the modifiable Bessel function of the form like this. It is important here that the a naught appears in the numerator, and for which we can apply the expansion of in around 0, because a naught is going to 0 for fixed a. Therefore, the characters coming from the spatial plackets are actually analytic in this formal a naught to the zero limit for a fixed a, giving no complication. The subtlety for the spatial placket arises when we take the continuum limit, taking both a naught and a, the spatial spacing to the zero at the same time, making G squared now run according to the renormalization group equation. In this treatment, which is required in extracting the continuum physics, we need to incorporate I epsilon also for the spatial plackets as argued previously. And by analogy, however, we can understand the role of I epsilon for the spatial plackets as recovering continuity of the field configurations in the continuum limit. And these are the summary, and I will just skip the summary. This will be the just a repetition. And as for the outlook and discussion, it is theoretically interesting that the I epsilon becomes required once the theory is formulated with compact variables. And the question is there a direct relation between the causal structure and the removable singular path? Okay. And the other question is that the 4D theory is seemingly highly entangled such that it is difficult to separate out the maximal torus degrees of freedom of both the time and space-like plackets simultaneously. the question is such separation possible? And if it exists, it will be useful to obtain the appropriate contour deformation. And for systems with compact variables, it has been discussed that the ordinary canonical operators such as phi and p phi, rather not u and p phi, cannot be defined straightforwardly. It was argued in these papers. And is there a relation to appearance of single paths? That's the question. And another question is, according to the argument relating Bessel's and perturbative expansion, non-perturbative effects, I mean, the e to the order 1/g² contributions in Euclidean, seems to be fully expressed by the numerical difference between IN and its asymptotic expansion. And therefore, I have a question that whether or not the instantons can be related to this expansion of IN. And we also need to set epsilon finite for a finite spacing A in Feynman kernels. And I'm curious if there is a similar care required in quantum computation. I'm sorry for exceeding a time a little bit. Thank you very much for that.
That's all right. Thank you very much. We're going to open it up for questions. First, I just want to say, of course, anyone who wants to leave because say they need to go to sleep can do so. I'm not going to stalk people and punish them for trying to sleep. But thank you very much, Nobuyuki. And if there are any questions, please just speak up. If not, then I'll ask. You referenced removing singular paths, several times. That the role of this I epsilon is to get rid of some set of paths which are pathological. Do you have like a careful definition of which paths it is that need to be removed? For instance, you mentioned winding number in the S1 case, but of course, if I was doing an S2 sigma model, right, fields valued on the sphere, there is no winding number anymore, and I don't think there is for SU3 a gauge series either, although I'm less sure. But certainly, like sigma models on most manifolds that I would want to do a sigma model on, most target spaces, don't have a winding number at all. So what is do you know what the actual condition is?
Thank you for the point. I don't have a precise definition, but according to the SU2 study over here, so I was having the same question on the SU2 because it is essentially S3 and how this winding can be identified. And if we treat the problem in this way, we see that this winding, we can identify the winding as this maximal torus of this group. So that is a part of the question, part of the answer I have. But for example, and for SU3, I imagine that there is similar relation so there are two directions of the torus for SU3, but so the winding can be defined, I believe, for these two directions. But for more
what do you mean by the maximal torus?
I'm sorry. So we can diagonalize SUN matrices as a diagonal matrix of the phase factors. But there is one constraint according to the fact that determinant is 1.
Gotcha.
So for SUN theories, there are n-1 direction of torus for this after diagonalization, and I refer to that as a maximal torus. And in that way, it is apparent. So the notion of winding becomes apparent. But as I noted in the conclusion part, it is uncertain how this winding can be defined when trading the spacetime uniformly. But I think yes, it is coming from this compactness of the groups, and I believe there is a generalized notion of this kind of windings, but I only have an answer in this simplified viewpoint yet. So yes, that is all what I can answer.
Okay, sure, thanks.
Thank you very much.
So can you give a comment on the last part that you mentioned to the quantum computation?
Yes. I'm okay.
Yeah, very last.
Okay.
Okay. Thank you. Yes.
According to this kind of argument, we need if we discretize time direction with a finite spacing A, it seems that we need to introduce epsilon and slightly rotate the coupling axis in order to obtain the correct continuum limit. If we use compact variables for a discretized system, so when I think when we construct the quantum algorithm for these kind of compact variable systems, I think we need to care that we do not see this global structure. So either we may not use the U states over here, or we may be able to implement epsilon.
This is a kind of wrapping around effect, right?
Yes.
And yeah, but I mean, so if we introduce a slightly, how to say, complexified gauge coupling, that introduce some non-unitarity.
Yes.
But it's not good for quantum computation,
yes.
I think.
Yes. So according to this argument, I think it is true that we may need at least a care, or yes.
So we have to lose some efficiency to get the correct continuum result.
Or if formulate everything with uncompact variable, that may be another option, but
that sounds difficult. Okay, thank you.
Thank you for the question.
Many on the quantum computing topic, some of the approaches to simulating gauge theories begin, they're not going to use a digital quantum computer. They say, no, we begin with this physical system where the Hilbert space is already naturally the wave functions on SU3. And it seems to me that all of the problems you've mentioned already exist in finding path integral formulations for those physical systems. That is, you're trying to find a path integral for the simulator itself, right? They have some atom or something which they say the Hilbert space is wave functions on SU3, and finding path integrals for that, you tell us is already problematic if you're working with the lattice because you need the I epsilon.
Hmm.
But then still, because nature, works, so to speak, even if we can't write a nice lattice path integral easily, taking those analog systems and saying, well, this is comparable to, I'm going to map the Hilbert space of this system to the Hilbert space of some lattice gauge theory. That step shouldn't have any problems, right? I mean, both are systems where the Hilbert space is wave functions on tensor products of SU3.
Mhm.
Right? The problem occurs only when I try to write down a path integral, which I don't try to do if I'm doing a quantum simulation.
Sorry, I got confused. Are you referring to this quantum computation?
Yeah.
Okay. And
right. So if my strategy for doing I don't remember, unfortunately, the names of the people working on this, but if my strategy for performing a quantum simulation with a quantum computer is to start with something which is already basically some set of particles wandering around SU3,
okay.
then yeah.
Okay. So if there is a quantum machine that has SU3 as kind of qubit, are you saying?
Yeah, that's
Oh.
the idea that there's some group in Europe, I think, that works on this
Oh,
sort of thing,
I
but I
see.
can't remember any names.
I'm sorry. Could you remind me of the question part?
Right. I mean, I'm trying to figure out if you agree or if you object to this story that I'm telling, that if you begin with a quantum device, it's going to be your quantum computer that already natively has these SU3 degrees of freedom, then you shouldn't have to worry about this I epsilon at all. The I epsilon comes in when you're linking to the path integral. If I'm just mapping one quantum system to another, nature has already implemented time evolution on SU3 as far as these people are concerned.
Yep.
I see. I understood. Okay. Okay. If we are able to evolve the system according to the exact Hamiltonian without introducing any finite time increments A, then I think everything would be okay. But the point is that if we, for example, introduce some shorter decomposition like approximation to the exact Hamiltonian, then we are dealing with the finite time increment A. And then we would see the global structure of the field space. And that may cause a problem, I think. And the nature is developing this system according to the exact Hamiltonian without introducing finite spacing, and therefore there will be that would not make a problem, as was the case with this first quantum mechanics system. I could deal with the exact Hamiltonian without introducing a finite spacing A, so I could obtain this correct amplitude without any subtleties. So the problem is whether or not we introduce the finite spacing A, I think.
Okay, thanks.
Thank you
May
very
I
much.
ask one question?
Yes, please.
Matsumoto-san, this is Kikukawa.
Thank you very much.
By the way, thank you very much for giving me to join this seminar, Scott and Yamauchi-san. Yes, and I have one question about this point. So could you go back to the slide 16, page 16, or the page you just showed? Yes, for the
64.
evolution kernel for the periodic quantum mechanics. Yes, yes, and one more page before. Yes, yes. So you said that this expression is ill-defined. It's not very defined. Yes, and
Yes.
but if you take the limit a goes to 0,
Mhm.
this gives just a periodic delta function for u and u prime. Do you agree on this point? Yes, so you can take the limit a goes to limit. Yes, then this expression just gives the periodic delta functions. Okay, so it is delta function, so this is a distribution, but I think it is okay in quantum mechanics. And yes, I agree that this evolution kernel at finite A is not a regular function in terms of u prime and u. But if you go to the momentum basis, this is it is very defined, right?
Yes.
Then it means that even if this is divergent with respect to u prime and u, so the configuration space variable, but the divergence, yes, it's actually divergent, but it simply says that we should treat this kernel as a kind of distribution for the compact variables. Okay, and we can you may introduce small I epsilon to regularize the distribution, making into the functions as in the Ito theory of distribution. But you can you can compute the physical quantity, partition function or correlation functions, and after that you can remove epsilon safely. Okay, so actually, so I think this is divergent, but we can treat it this divergent nature by regularizing by the method to regularize the distribution. Okay, theory. So I don't think it is not ill-defined. Divergence means that we should treat this evolution kernel as a distribution. Okay, for the compact variables, quantum mechanics. For the non-compact case, we are lucky because this is actually the function, not the distribution, and it becomes distribution or delta function only a goes to only the limit a goes to 0. But at finite a, it is given by the Gaussian function with not the Gaussian, but Gaussian very oscillatory but Gaussian function in terms of x and x prime. Okay, so I think divergence is okay. We can treat as a distribution. This is my point of view. And so yes, and in fact, if you go to the Fourier basis or momentum basis, it is completely fine, and you can do any computation in the quantum mechanics.
So, okay. Would you say that?
Yes.
I agree that for a equals 0.
Yes, it gives a periodic delta function.
Periodic delta function.
Yeah, for u prime u.
For finite a,
yes.
did you say that this can be given a distributional meaning?
Yes, I think so. Because if you go to the momentum basis or momentum basis, we can do this. We can any computation safely, and this means that yes, we can do the similar computation by treating this as a distribution.
And
And you may introduce I epsilon, but you can, yes, and make the distribution to the functions and continue computation, for example, by path integrations. But after that, you can remove the epsilon. You can set epsilon 0 safely without taking the continuum limit, or A goes to 0 limit. You can obtain the desired result which you showed first. Yes.
thank you. If I understand correctly, for example, in the delta function case,
Yes.
we would see after summing over small n, the momentum modes, we will see appearance of delta function like peaks, and
Yes.
other places there will be
Yes.
0.
Yeah.
In this case,
Mhm.
such peaks are not seems for me not appearing. So this is delta phi direction. So
Mhm.
If
Yeah.
for
Yes.
such a-
Yes. At finite, it is not a delta function. Okay.
Mhm.
Exact delta function. So some weight in terms of delta phi. But we should treat it as a distribution. And once, so if you want regularize the distribution, you may introduce I epsilon. But and you can perform the computation. But after that, you can remove the epsilon. You can set epsilon goes to 0 safely to reproduce the quantum mechanical results.
I see. Okay.
Yeah. So, okay. So this point is very different from using the Wilson discretization exactly on the or in the real-time direction with small epsilon. In this case, you cannot set epsilon goes to 0 before taking A goes to 0, right? As you said. So it's very different behavior. So for the Wilson case, epsilon has another role to suppress the imaginary or second non-regular part or divergent part of the asymptotic expansions. Okay, so the meaning of epsilon is very different, or the role of the epsilon is very different, I think.
Thank you very much for that. Could you remind me of the functional theory that deal with distribution, like
Yes.
object? Did you say Ito?
Yeah, Ito theory of distribution, and they introduce I epsilon to regularize the delta functional singularity. So we can do the similar thing if you want to escape this kind of divergence. Yes.
Thank you very
And
much.
for the non-periodic usual quantum mechanics, this evolution kernel becomes a function happily, and it behaves delta function in the only in the limit A goes to 0. Okay, but for the periodic case, at the finite A, it still remains distribution, but we can treat it if you treat correctly, and we can reproduce the quantum mechanical result with yes, which is defined before we consider the path integration formalism. Do you agree?
I'm
my
not.
point?
I think I understood your comment, but I'm sorry that I do not know much about the Ito theory or this super function like treatment. I would like to yes, look into the literatures to study these techniques. But yes,
So I think for the periodic variables, this evolution kernel is divergent, and it is not good if you try to define the path integration with finite action with respect to u and u prime. But for quantum mechanics, there is nothing wrong with this evolution kernel, even if it diverges for the compact variables. And then, as to your comments on the quantum computations, I don't think you need to introduce epsilon. Yes, if you have a unitary theory, then you can do. Although it is a compact continuous variable, so you should go to the momentum basis at least.
So
to have a discrete variables, but you can do, and then you need to truncate the Hilbert space also, but then you can do the unitary computation, I think.
Starting from, not starting from the configuration U states, but in the from the momentum states.
Momentum space, everything is okay, I think.
I see, yes.
So yes, so this is why there is a way to treat this divergent evolution kernel in terms of u and u prime. Yes, so there is so we should think it is given by a kind of distribution for the compact variables. It is not the present situation, but we can treat it as a distribution. Yeah.
The point is that there is a well-defined unitary evolution in the momentum basis.
Yeah.
And therefore there is a method to map it back to the configuration basis.
Yeah.
Okay.
Yes.
Thank you very much. I understand.
Yes. So there should be a way to treat even it diverges. Yes.
Thank you very much.
Yes. So this is my point of view. Yes.
Thank you very much.
Yes.
I agree.
And in anyway, if you want to do the computation in path integral formulation, we need to define the action as a function of the variable which should be integrated. So as you said, we should introduce I epsilon in any way to regularize distribution into the function. Yes. But after if you have a unitary theory, then after the computation you can remove epsilon safely before taking the continuum. Yeah. So this is my point.
Study and understand more further.
Yeah. So
thank you very much.
In this point, it is very different from the Wilson discretization action for the real-time direction. Yes. In this case, you need to epsilon to remove the unwanted part of the asymptotic expansions.
I understand.
And if you do not remove this part, you cannot reproduce even the Kogatsu-Susskind theory. So that is your point. Right?
Yes.
So yes.
Thank you very much.
It has more role, I think. Yes.
So very valuable discussion for me. Yes. Thank you very much for the information.
Yes. Thank you very much.